So continuing on. All right, so this is the principle of equivalence. Okay, inertial mass is the same as gravitational mass. Why it is so, it's kind of complicated, but as far as we can tell, they seem to be the same. This part, chapter 13.4, is just talking about how you can get little g. The 9.8 that we've been using all this time really just comes from the universal gravitation. You take the mass of the Earth, you take the radius of the Earth, you take the gravitational constant, you'll get 9.8. This actually kind of shows different little g's for different altitudes. Right? You'll find that it goes significantly lower as you go further and further away. Be mindful that this is an altitude. So this isn't like 30 times the distance. This isn't 30 times r. The radius of the Earth needs to be added into this, which is, where was it? 6. No, you will not need to memorize that table at all. Here's some kind of astronomical data. So if you're looking at like the Earth, right? The radius of the Earth is like 6 million meters. And that's just the radius, right? So you take your 6 million meters, and now you add your 300,000 meters. It's not much of a change at all, right? Only when you get into additional millions of meters, then you start losing gravity really fast. Okay. Any other questions so far? Okay, so just recapping. We got our laws, Kepler's laws, talk about orbit. Newton's law of gravitation tells us how things are pulled towards each other. That's really about it so far. All right. Chapter 30 or 13.5, you can skip for now. Okay, this is where you're talking about potential energy. You see all this integral stuff. We're not doing that yet. Okay, I was checking with Mr. Buck, and so I was looking at the Calc AB schedule. You guys do integrals pretty much through February. So once you guys are done with that in February, like kind of towards the end of February, we can go back and revisit all the integral stuff, and you can look at it and be like, oh, that makes sense, I hope. Okay, so don't worry about this yet. If you want to read through it, I mean, I'm not stopping you. You know, it's a good head start. But you may find it pretty confusing, especially when we talk about potential energy for gravitation. It's a little weird. It's always negative, which can be, it's a weird concept, but it's always negative. Okay, what I do want to continue with though is chapter 13.6. Okay, so when you're looking at the notes, right, 13.1 through 13.4 and then 13.6, you need to know. So I had said that when we look at these orbits, we're going to look at circular ones. So let's look at some of the consequences of circular orbits. Because it is circular, that means that your acceleration is only centripetal, and that is due to the force of gravity. And because it's circular motion, there's a relationship between this tangential velocity, this should be a t, and this centripetal acceleration, right? So how quickly you turn is directly related to how fast you're going. And if you substitute everything in, you get this conclusion that for a circular orbit, your velocity must be a certain amount. This square root of gm over r. If you do it for the Earth, we can do that real quick actually. Square root. Okay, so for the Earth, I'll do square root 6.67 times 10 to the negative 11. By the way, as far as memorizing this constant, you don't have to memorize it. It's on your equation sheet, but it can save you time if you do memorize it. Just like Avogadro's number, right? 6.022 times 10 to the 23rd, that kind of thing. Or there's a couple other constants that can be really convenient to know. All right. So that times the mass of the Earth, it was like 5.98 times 10 to the 24th. divided by the radius of the Earth, which was 6.37 times 10 to the 6th. Whoops. And you get something like that. So about 7.9 kilometers per second. Okay, so 7,913 meters per second, or almost 8 kilometers per second. That's how fast you have to be going if you were at the surface of the Earth, okay? At the surface of the Earth. Like a bullet that was trying to do a circular orbit around the Earth. That's how fast you have to be going. Notice that the further out you go, the slower you have to go. Okay, the further out you go, the slower you have to go in a circular orbit. Yeah, I'm trying to think. Right. So when you're talking about like the International Space Station, that's going maybe more at like 7.7 kilometers per second. Still going pretty fast, right? It's going fast so that, see, if you look at some of these values for little g, go back. If you look at these values for little g, it's not that on the International Space Station, again, it's not that there's zero gravity. There is gravity. They are accelerating downward. But because they're going so fast, right, 7.7 kilometers per second, they are turning as fast as they are falling. And so when we say that they're weightless, it's not that there's no gravity pulling on them. It's that they're going so fast that they're falling all the time. And so that's why it appears that they're weightless. So, super important concept. Okay. So from that outcome, I will tell you that on the AP exam, most of the kinds of questions that you'll get regarding universal gravitation is taking this law and doing all sorts of just different proportional thinking. So if I double the mass, how does my tangential velocity change if I want circular orbit? Or if I double the radius of my circular orbit, now how fast am I going? Or if I double the radius of my orbit on a planet that is 1/4 the mass, and a bunch of random stuff, right? If I just change all these numbers, now what happens? And sometimes they won't even phrase it in terms of the velocity. They'll say, okay, now what's my orbital period? So you gotta relate your velocity for your circular orbit to your angular velocity, which is then related to your frequency, which is related to your period. So there's all sorts of circular motion stuff that comes up a lot for this circular orbit stuff. So all the rotational kinematic stuff, right, will come up. So just keep that in mind. They're quite related. Okay, questions so far? Where this comes from? How to calculate this? I think the math isn't super crazy. It's not like the elastic collision stuff. That was pretty bananas. Okay, so if we assume circular orbits, okay, now we can go and investigate Kepler's laws and look at the math behind Kepler's laws. We're skipping second law for now, but if you look at Kepler's third law, okay, Kepler's third law said that your period, the orbital period, how much time it takes to go around once, the square of it is proportional to the cube of the radius. So if I double my radius, I get the square root of 8 times as much period. It's a little weird, right? But you take the 2, you cube it, and then you take the square root. What was that? Root 2, no, 2 root 2, whatever. So then how do we prove that? Well, let's actually go through those steps. How do we prove that it's supposed to be that way? It actually really just comes from this. Because if I know it's a circular orbit, and I know that from my forces, I can demonstrate that my tangential velocity has to equal to this, but my tangential velocity is related to my frequency, and my frequency is related to my period, then that means my period must be related to my radius, right? considering the same planet. So let's go through some of that math. Start from here, right? I wrote M1 in here. I'm just going to try and use the book's conventions. I'll use big M for the mass of the planet, whatever the... A lot of this, too, when we talk about circular orbits, assumes that you have one significantly more massive object than the other, right? So we're not looking at two binary stars. We're looking at like a planet and a satellite or a spaceship or something like that. Okay, so let's make our substitution. I made some mistakes earlier, but if your tangential velocity is equal to omega r, and then your angular velocity is related to your period, we can make that substitution. Or another way to think about it is your velocity is like a distance over time, right? So if the time is one full circle, how far do you travel in one full circle? You travel one circumference, 2 pi r. So your velocity is your circumference per period. So all these results are validated. That's equal to this. So now I just want to solve for r. Right? How does r relate to t? So I'll get the r's on one side, t on the other side. So I multiply t over and brought that under. And you flip. And then the next step, I square everything and combine like terms. Not combine like terms, but whatever. And then you can demonstrate that t squared is proportional to r squared, or r cubed. Right. And again, this was specifically for circular orbit. The way you would go about showing it for an ellipse is quite different. Ellipses behave really complicatedly. Right. Okay, so as far as the AP exam goes too, this equation is not on your equation sheet. And they may ask, I've seen in the past that they ask students to show this. You will need to know how to go from here to here. Or actually, really, you need to know how to go from here through all of this, all the way through here. And all of it really is just circular motion, actually. The main substitution is this one. And then when you do the algebra, you get to here. And then the next substitution is, I would guess, I suppose, kind of these two. The Vt equals to omega r. And then you can get to, the algebra gets to here. So I know this is like a whole bunch of stuff. This always happens at the beginning of the unit. We'll get to some practice pretty soon. Okay, so this is Kepler's third law. This is the third law. The third law is the proportion, but you need to know how to get to this. All this coefficient stuff, the 4 pi squared over gm for a given planet, those will be constant. Okay, questions on that? Okay, let's try a practice problem. Practice. When I was doing this earlier, Mastering Physics was down, so I kind of just picked a random one from the back of the book. Let's try number 4. Number 4, a 1 meter diameter lead sphere has a mass of 5,900 kilograms, so it's a very big sphere. I wonder if the density actually works out for that. It's 5,900 kilograms. It's really heavy. A dust particle rests on the surface. What is the ratio of the gravitational force of the sphere on the dust particle to the gravitational force of the Earth on the dust particle? How do you figure out that ratio? Give it a shot. feel free to work with each other. Talk.
The ratio gravity force of a sphere.
1 meter. This. But it's lead.
If you take the gravitational constant, multiplied by the mass of the sphere, it's 5,900 kilograms, divided by the radius. What is that?
For this problem, you may need the astronomical data here. So I'll put it, there's the mass, there's the radius. I can help.
What? Versus the and then you do energy. And she's like, no, it's too and it was for nothing. No, so that's what So you're staying here then? Your mom like does what? I can't go, but make sure with both of them. Yes, you can. I know people have taken it so much. Different in China. The Japanese. No, I totally do. I have not seen this time. It's just like, wait. Oh, are you like on like just 16 years?
I don't think so.
But the other one is the real thing. This is actually.
Oh, okay. So this will make the number. Putting it as 0.5 will make the number larger.
Wait, is it like
Then do I have to time this myself? I thought it was it's
I don't know. Now it's like
Alright guys, folks, let's take a look. So you're looking for the ratio of the forces. Okay. So I was lazy, I didn't really want to label every single thing. So you have GMM over r squared for the sphere divided by GMM over r squared for the Earth. You'll notice that they both have the same G, that cancels out. It's still the dust, so one of those masses will cancel out. Whatever one represents the mass of the dust, will cancel out. So really, you're just looking at the ratio of mass of the sphere divided by its radius squared, divided by mass of the Earth by its radius squared, which gives you this. Okay, that's it. Any questions on this problem? Or four? Yep.
Why don't you put the gravitation constant in the first part of the...
Because it cancels out.
Oh, right.
Because you're looking at the ratio. So it doesn't matter. So this is where I say, if you can do your physics symbolically every single time, you will save yourself a lot of calculation. Because I saw a number of you guys calculate this one first, then you guys calculate this one second, and then you divided them, and you end up, especially because now the constant is, it's not just 9.8, it's the 6.67 times 10 to the negative 11. It's going to make your numbers look really weird. Weird just meaning like they're cumbersome, you know? So whenever you have an opportunity to cancel them out, the better. Okay. Questions? Questions? Okay. So this is just kind of an example of using Newton's law. You'll find that there aren't that many questions, mathematical questions for Kepler's laws, except for messing around with this. Okay, this comes up a lot in terms of changing the mass, or given the period, you have some radius, whatever, right? Whatever algebraic manipulations dealing with this, this comes up. Or the next concept, the last concept that we're going to deal with is Kepler's second law. Okay, so we're backtracking a little bit. Kepler's second law is a little tricky, so I want to take a little time to talk about this one. Fundamentally, when we say that it speeds up as it gets close and it gets slower as it gets further away, it just comes down to conservation of angular momentum. That's all it comes from. This is a mathematical proof of it. I'll give you the shorthand, but I want to explain some of the math that's going on here. So first, I want to look at this. L equals mRv sine beta. And I want to explain why they have this sine beta. What makes elliptical motion so difficult is that you have now both radial velocity and tangential velocity. Circular motion is really nice because you only have tangential velocity. You have your radius does not change, right? But when you have an ellipse, sometimes you're moving away and sometimes you're coming closer, which means you have both. And as we'll see how that influences the energy and how that influences, and not only that, circular orbit is really nice because now your radius is constant, which means that the force of gravity is constant because r is not changing, your masses aren't changing, your force of gravity is not changing, that means your acceleration stays the same. Circular orbits, everything pretty much stays the same. Once you have an ellipse, you're moving away, which means that your radius is changing, which means that the force of gravity on you is changing, which means your acceleration changes, which means that the rate at which you go away changes, which means that your velocity rate of change will change, right? And so not only do you slow down as you go further away, the rate at which you slows down as you go away. And as you come closer, not only do you start going faster, but the rate at which you go faster becomes faster because you're closer and your acceleration increases and all that stuff. So that's what made Isaac Newton have to invent calculus to figure it all out. It gets pretty complicated. But there are some easy things that we can pick away from this. One is when we look at angular momentum, if we look at your velocity at any given moment that's going along this ellipse, if we can split it into a component that is perpendicular to this radius vector, okay, I say it's a radius vector. It's not a radius. Technically, I guess I should say it's your position vector. It is the vector that represents the line from your focus to where you're at. Your velocity perpendicular to that, we will call your tangential velocity. In other words, if you can split it into two parts, what part of your velocity is moving you away and what part of your velocity is turning you? Your tangential velocity is the velocity that's actually making you turn, and then your radial velocity is what's making you push away, right, or come closer. Your angular momentum is only relevant to the turning part. In other words, let's say you have the Earth, right? The moon goes like this. If I launched a rocket that went straight away from the Earth, without orbiting the Earth in any way, just perfectly straight away, that would have no angular momentum relative to the Earth, right? But any rocket launch that we have, it doesn't go straight up. It goes like this. You turn your radial velocity into a tangential velocity so that we can establish circular motion. Because you need to have tangential velocity to keep you in this falling motion, so on and so forth, right? In other words, we don't send rockets to go up and have to fight gravity by constantly firing its boosters to just stay floating there. Instead, what we do is we launch them up and we turn them so that once they start going fast enough, they can constantly fall without ever falling. And then they can turn off their boosters. They don't have to use any engine power whatsoever, and they're just constantly going in circles. Does that make sense? Right? That's much more intelligent than trying to get a rocket to just like float there in space. So your angular momentum is really only dependent on that tangential velocity. That's where the sine beta comes from. You're looking at the component of my velocity that is perpendicular to that position vector. So at any given moment, that gives me my angular momentum. So Kepler's second law said that it sweeps out equal areas in equal time. So that's the next step. How much area is covered in a certain amount of time? You're looking at the triangle. Is an approximation, right? Because technically it's curved, right? Your path is curved. But if you look at a very small increment, you can kind of represent it as a triangle. It's an approximation, but it works out. As you take the limit, a lot of times that's what we do. We take an approximation and then we use calculus to say, okay, as the limit it gets smaller and smaller and smaller, what is the limit as that height gets to 0? And you can show that you get the same result. But in any case, you'll find that this sine beta comes up again for how much area you cover in a certain amount of time. And ultimately, again, now this part you don't have to drive. Okay, you don't have to know how to drive this. You only need to know that when all is said and done, the amount of area you cover divided by the amount of time you give it ends up being a constant value, which is related to your angular momentum and the mass of the sorry, it's not even the mass of the planet. It's the mass of your object, of the satellite. So actually, yeah, I think the mass will cancel out somewhere in there. But either way, it's just dependent on your initial angular momentum. Okay, it stays constant. That's all that matters. This is a conceptual question. On the AP exam, you probably won't get any. Well, if you did get it, it would still be for a circular orbit. And once it's a circular orbit, all this stuff becomes much simplified. Okay, so, but you probably won't get any sort of calculation problems for this. It's going to be very conceptual. Okay, so that's Kepler's second law. Okay, Kepler's second law is just based on conservation of angular momentum. Questions? Okay, so that's pretty much it for chapter 13. I want to spend some time on Monday talking about what was presented here in terms of fields. Okay, we haven't talked about gravitational fields at all, or how to represent it mathematically. The book doesn't either, but I want to do it because it will lead into electric stuff very well. We still have like 5 minutes. If you want to put your stuff away, that's okay. But what I want to do is show you an example AP problem and see if you can at least feel like you understand what you're supposed to do.